The presentation is split in two parts. I present part one, general introduction, so is related to this particular algorithm and principle, and more applied with the more applied approach. And the second, so general introduction, and the second part with more mathematical insight will be performed by my colleague Fabiana Zama after my presentation. Before I start with introducing the background where this principle was developed, because terminology and also some approach are specific to the area where this was developed, in particular rocks, porous media. Okay, origin of open uniform penalty is the definition, and then was conceived by Bob Brown in the 80s, more or less, of the last century. Bob Brown was a friend for me. His start his research activity and at Los Alamos in Manhattan Project as a young engineer, electronic engineer, then worked at what is now Chevron, no? Oil companies. And the origin of the activity of Bob describe the development and the terminology in the background of open. So this is the algorithm the software we developed around the original open algorithm, and the idea is to obtain good tools to fit the data, and then we try to explain in a very easy and simple, so approximated definition, what we say in a simple way, robust algorithm to understand the different spin population inside a sample. About the theory, before the presentation before this has already introduced the concept of spin, the concept of relaxation, T1, T2, etc. So I assume you are able to know this physics concept. In few words, just to have a classification, rough classification of NMR, we can split NMR in imaging, MRI, in spectroscopy, and in relaxometry. We are working in relaxometry. Relaxometry, again, can be in another rough classification divided in two areas, a fixed field or a not fixed field, so fast field cycling. Background terminology, the same concepts are developed in many different areas. Each area has a different definition for the same things, same object, or different name, or same name for different object. Okay. In the following, we follow more an approach, more engineeristic point of view. And so we have the real system, so the physical system. In our case, the spin inside some sample. Sample could be of many different kind. Can be food, can be biologic, can be
Sample can be used, can be biologic, can be used, biologic, can be used,
there is a lot of echo. There is a lot of echo. There is a lot of. Can you hear me? Can you hear me? Can you hear me? Probably there is some microphone open. Okay, we stop it. Okay, we have a real system. A system is characterized by some internal evolution of the system and some parameter. There are some parameters that characterize the system. Parameter, for example, can be in case sorry, devo dire che c'è un microfono acceso e io sento un gran eco. Some parameter, for example, can be in case of porous media, porosity, permeability, etc. We we need to understand what happens inside the sample, so the real system, the phenomenon, the process occurring. And so we develop a simplified object called mathematical model. Mathematical model is a object try to reproduce some behavior of the system, okay? The model is not a clone of the system, it's just a simplified version able to reproduce some behavior. So in general is an equation, differential equation, etc. Depend on the systems and depend on the field. This, just to have an idea, is an equation for an aquifer, just to have an idea. Artesian aquifer. What is of interest? It is necessary to extract from the sample in order to use the mathematical model. Just to be sure, the mathematical model is robust and is representative of the system. So the output of the model, mathematical model, should be equal to the output of the system once it is excited with some input. And this is not so easy to understand if your mathematical model corresponds to the behavior of the system. It's part of the research. This. Okay, we need to give some value to the parameter. Parameter, how? Comparing, so parameter estimation, so the fitting procedure. In a more general terminology is a model calibration, okay? We need to compare the output of the mathematical model with some data acquired on the system. So in order to have a correct calibration, it is necessary to have good data. Model calibration is an ill-posed problem. So if you have bad data, you obtain very bad output from the use of a mathematical model. So an extremely important aspect is the experimental setup. In order to correctly understand the work, the behavior of the system, you should have a well-designed experiment, because otherwise your model can fit the data, obtaining a bad result and can confuse the researcher. Okay, background of open. Open software is so an inverse software for inverse problem. In order, and it supposes its kernel, so the mathematical model, is multi-exponential. Why this origin? Because theoretically, it is supposed this one whose media origin was rocks. So inside rocks, you have pores of micrometer size, no? Very, so 10 to minus 6 meter order of magnitude. Okay. Inside, you have a molecule are moving inside, touching the surface. The molecule relax. This one is called diffusion cell. This is a reference in which you want to go more in detail. We are in the 60 or 70 of the last century, just to have an idea of the period was developed this theory. And so it is possible to theoretically demonstrate that the rate of T2 or rate of T1, so the inverse of relaxation time T2, transversal relaxation time and longitudinal relaxation time T1 are related to these quantities. So bulk relaxation here, far from the surface, a term depending on the relaxation closer to the surface in a thin layer on the surface of pores, and a term due to the diffusion inside the gradient. I remember the experiment, NMR experiment relaxometry, there is a fixed gradient, a fixed magnetic field polarizing the spin, and then excited with radio frequency pulse. These are flipped, and then they moving inside, touching the surface due to the gradient inside the sample, relax. Or T2 bulk is a connaturate, natural relaxation of the nuclear magnetic resonance phenomenon. T1 does not depend on diffusion, just T2. If we suppose that diffusion, so we are in fast diffusion regime and fast exchange regime, then what remains inside is just a term depending on the relaxation on the surface. So inside a sample, what we have are, for example, a rock, many different diffusion cell. So each of these, each of these is a population of spin. So this one relax with typical T2 or T1 if the experiment is T1. This is another population of spin. This one is another population of spin. So we have 5 population of spin, 5 in this example, okay? 5 population of spin. So fitting this data, I suppose that we have a multi-exponential kernel, no? Mathematical model, in this case with 5 peaks, 5 exponential. And so comparing the data using a fitting algorithm, I should be able to obtain the magnetization, so the amount of population in each of the 5 spin population and the corresponding T2. To work on this, okay, so in general, this is background. Open was developed working in the oil field at the origin and then expanded to other materials, kind of materials, biological, food, cement, etc. But the background, the model, the kernel on which it is supposed the phenomena inside the sample are occurring is multi-exponential, like this. So we needed to comparing the experimental data, good experimental data, with the model, the algorithm, open in particular, try to obtain a value for F1, sorry, I have to, okay, F1, the amplitude, and Ti, so T1 or T2 depend on the kind of experiment, CPMG in general for T2, or inversion recovery or saturation recovery for T1. So there are 2 parameters should be obtained in the calibration of the model, no? In the fitting procedure or regression, nonlinear regression. The terminology change substantially from different disciplines sometimes. So our model is characterized by its parameter. We have 2 approaches. Also, this in a very rough description. More mathematical detail will be done after by my colleague Fabiana Zama when I finished. So we can fit this data using nonlinear fitting with a nonlinear algorithm, no? Okay, in which both F and Ti are regressed, or in a linear or best quasi-linear, quasi-continuous, quasi-linear fitting means we fix a number of Ti on a scale, no? Inversion time, T1 or T2 depend on the experiment, and then the algorithm simply determines the amplitude. This one is a linear fitting. Why quasi-continuous? Because we have a discrete number of Ti. On the axis of the relaxation time, we have an infinite number of possible Ti, and we select a number. 41 in general is in a logarithmic scale. Instead, for T2 is in linear scale, and the distance between the 2 is echo time, no? In a CPMG experiment. So the real data acquired, so S time Tj, is the model, but there is also an error. if we have not some particular problem in the data acquired, this is just the experimental error. So with the distribution Gaussian, because it is the typical experimental error when you perform any kind of physical experiment with the amplitude of the Gaussian error depending on the quality of the experiment performed. But sometimes, often, you have some distortion of data because the magnetization field is not homogeneous correctly, because it's not stationary. The field means over time the polarization field changes not only by position in the sample, but will change also in time. Some glitch, electronic glitch. So in general, the error added is far from a pure noise, Gaussian white noise. This one, by mathematical point of view, this quasi-continuous linear fitting is a freedom integral like this, with a kernel like this. Now, the procedure of fitting, so the procedure is, I have experimental data, I compare the experimental data with the model, and the algorithm should be able, no, is a least square minimization, should obtain, in quasi-continuum, should contain this term. What is the main problem? Is in general, if you use just this approach, no, a square regression, you obtain a very bad result. What is the final aim of an inversion? So extract the parameter. You want an estimation of the parameter, but you want also to have a parameter error estimation, no? An interval of confidence around each parameter in order to evaluate in case step back. What is the typical use of NMR? You have a sample, for example, a cement. You prepare the cement. The cement over time is as occur hydration, so is increase is move from liquid to solid structure, gel structure. And so you measure after 10 minutes, after 2 hours, 3 hours, etc. And so you are able to follow the evolution of the hardening of the cement, for example. Or you can evaluate if you flux a rock sample with water, what happens to the permeability of the sample, a petrophysical property representing the attitude of the sample to allow to the fluid to move inside, etc., etc. So it is not enough to have just the value of the parameter, but you should also know if the same parameter computed in two different moments, in two different experiments, how can be compared? Is the same with a different error, so is the same value, or the bar, no? The confidence interval is so different, you can say, okay, the parameter is changed over the value, the parameter is changed over the time. And another information should be about the goodness of the fit, because one of the big problem of inversion is ill-posed problem. To be in a discrete field is more correct to say, but Fabiana will explain better after, is ill-conditioned problem, because it's discrete and not continuous problem. And so you can have theoretically infinite model equal well inside the experimental error can reproduce your experimental data. And so you have to choose among all these possible model, what is the model you want to use. In order to do this, so you need a goodness of fit. In order to discard the model, you suppose the model in this case means the set of parameters. You have just one model, multi-exponential, but you can obtain very different set of parameters when you compare, you fit one set of data. And so you can introduce, you need to introduce a priori information, constraints, for example, non-negativity of the distribution, for example. These information a priori are information is the user knows about the sample you are measuring. You are measuring cheese or cement is different the structure of the sample, and so the constraints you suppose are valid are different, and the user should know exactly what is working with. Another information typically used is the parsimony principle or Occam-Razor principle, means among all the possible solutions obtained by the fit, you choose the solution with less detail, because statistically, if you assign a probability to each detail, as the final probability to have a distribution is the product of this probability, the solution with less detail is, if it works correctly, clearly, among two fitting equally well to see, the one with less detail is the most probable by statistical point of view. So the algorithm, the implementation, the final implementation of an algorithm should satisfy all of these requirements. In order to fit una direct fit is impossible, a typical approach is to add to the algorithm of minimization not just the comparison of the experimental result with the model, but just to add a regularization term, where lambda is a parameter defining the strength of the regularization term, this lambda, and this one L is an operator, can be amplitude, can be slope, so first derivative, applied on the distribution itself, or the curvature. Open is a L to regularize the Tikhonov like least square quasi-continuous linear problem. So use L with the curvature of the distribution. With another, this is called a cost function. So at the end, the algorithm should minimize the cost function. What is the main difference of open respect to this one, the Tikhonov regularization, where you have just one lambda? Open, I'm late, introduce not just one lambda, but many lambda. And so the lambda are, this one is a typical distribution of relaxation time T2 in this case obtained using open. Open set the lambda to each point, so is locally adapted penalty function. This is a particular idea designed, invented by Bob Brown, no? The person I introduced at the beginning, defining the open principle. Another very important part of the invention is the diagnostic and option of the algorithm, because following what was described before, it is not just enough to have a distribution, but also have some information about the error and about the quality of this. This one is a more mathematical sound representation of open principle. So you have already in discrete format. So you have the fidelity term, so the comparison of experimental data with the model, and the regularization term. You need to decide how to use, because you need to evaluate lambda locally. You see now lambda is not unique, but there is many lambda equal to the number of points of the distribution M. How compute using the balancing principle. So the error of fitting for the penalty terms and the regularization term, this should be equal This one has been demonstrated, can be demonstrated, and also Fabiana has demonstrated this, is possible to show that if you use a balancing principle, this minimization converge to a result. This one is a uniform penalty invented by Bob. This is how the single local parameter of regularization are computed comparing this and this. Okay. Inside, you see in the algorithm, there are three meta parameters. So means we say, okay, in the typical Tikhonov, you have one lambda, you have to determine this lambda using many different approaches, the corner approach, the L curve, that is difficult. Open principle automatically compute using by itself, compute this lambda. But we introduce, nevertheless, some parameter, compliance parameter, because this parameter characterize the kind of sample. So if you are using, for example, cement, or you are using milk, are completely different sample, or you are, so the amplitude of the signal you obtain from the experiment is completely different. If you are using a different instrument, you have different gain, different information, and so these are meta parameter, can set correctly, so trigger this, the approach of Uben, so a specific kind, no, of samples and instrument. Once you have this, for all the experiment, automatically it works by itself without the necessity to directly evaluate the regularization term. This is a typical distribution of open, and the main goal at the origin was conceived by Bob to have Bob Brown, Bob for friends, is to have an algorithm allow to identify separate peak, no? Sharp peak, and broad features without split all the broad feature in many peaks. Consider that the area below the peaks correspond to one of the spin population of the beginning, no? Correspond to a diffusion cell inside a rock. If you are in respect to the example shown before, this distribution should have 5, you remember, 5 separated peak, because we have 5 independent, not exchanged population of spin. So it is mandatory to have an algorithm is smart enough to do not split peak, in which the data, the signal to noise ratio of the data does not allow to separate in many peaks. At the same time, do not include a single peak with another peak. OpenWin works properly in this field. Another things I didn't explain, we are working 1D dimension, so CPMG, inversion recovery. And we developed a set of software based on Open, working on 2D, T1, T2, T2, T2D, diffusion T2, etc. And also for working with NMRD, fast field sampling at the same time. And when you run Open, you obtain also a set of information about the noise, the comparison, the skewness of the error, so to qualify the goods of the result, and indirectly also on the quality of the data. Remember, garbage data input, garbage distribution in output. If you have bad data with bad experimental performance task, you obtain a strange result. And as the interpretation of the distribution allow you to understand the behavior of the sample, no? Your comprehension of the sample increase, you can be confused and have obtain wrong, no? result. OpenWin in detail, very fast. Around the algorithm, we developed a software. Software is marked OpenWin specific by University of Bologna. This was in 2008, the period. But we show very briefly after, we created also other software, free, can be downloaded by the Unibo, from my department web page. I show you after. So this is more or less the evolution of Open over the time. With Open, other two persons involved at the beginning in the development of the Open to test, to validate, verify, etc., was Giulio Cesare Borgia and Paola Fantazzini at Department of Physics, University of Bologna, my department, DICAM. There is what is called a magnetic resonance porous media lab. And on this also dedicated to this in the 91, in this lab started the series of conference magnetic resonance in porous media, Bologna conference, international conference in porous media. The kernel, the evolution. The evolution is to extend in 2D the open principle. This was performed by me with Fabiana Zame, other colleague at University of Bologna. Then I will list all the participant guys. This is a typical algorithm implemented. That algorithm 2D is not need to also use gradient projection, Newton projection, conjugate gradient, etc. Use other algorithm, and the detailed description of this will be performed with more mathematical sounding, by Fabiana after. The code was validated 2D. This one is T1, T2 maps, you see, with synthetic data, and compared. So validation and verification is the typical activity performed on model and software when you perform. These can be freely downloaded by, as told before, site unibo.it, software DICAM, DICM is my department, etc., are freely usable. We extended more, also adding another regularization term, because in 2D the problem is isolated peak using just the open, translating from open 1D, this term, has some problem to identify isolated peak. And so we also added a term using the amplitude, this term, with another, not local but global, regularization parameter. And we call this MUPEN, multiple uniform penalty. Also this, the algorithm performed inside, explained by Fabiana. We test with many different software and real synthetic, real data over the time. And we add also some information about the statistic in order to have an information about the quality of data. If our fit is correct, the residual, the error, the difference between, for each point of the acquired data, you have a point computed by the software. The difference is the residual, should be distributed if everything goes correctly, following a Gaussian distribution. Gaussian, not too large, no? The amplitude at the half 8 represent the confidence of interval, the deviation standard, and so in using this you have an idea. And also, if it's not distributed as a bell, typical of Gaussian, means there are some distortion. And this is a bell, no? A ring. You need to check your data, or you have to check some parameter used by the algorithm for inversion because something goes wrong. This is the software. There is also a guy, graphical unit user interface developed under MATLAB, is a compiled version. Also, this can be downloaded for free from University of Bologna. We also collaborating with other colleagues, in this case, University of Padova, we applied Open, our software, free software in this case, 2D different kernel like this. This one it was capture emission, electron capture emission time trap because it was of interest for the creation of semiconductor materials. We implement a version of MUPEN 1D for analyzing. The detailed theory was described in a very good and enhanced description before by Professor Danuta, and we implemented this simple multi-Lorentzian kernel in order to fit to fit the NMRD profile using what is called the model-free kernel approach. Model-free approach. Model-free approach. Some users raise some question about the correctness of fitting the data with this kind of a model. Consider that the model represents the process occurring in the sample, and in order to evaluate correctly the result of a fit, you should be sure your model is valid for the phenomenon of the sample. And this one is the main core of the reasoning of the research. Also for this, we have developed an interface standalone GUI software downloadable from the Unibo site. And for this, using Monte Carlo evaluation, simply given the data, experimental data, NMRD profile, we add some noise, the Gaussian noise in a specific range. We add many times, so we create, starting from the original acquired experimental data, we generate many different synthetic data, simply adding Gauss noise, and we perform, this is performed automatically by the software, no? Is this one, Monte Carlo analysis. In this screenshot means 50 times this operation is repeated, and so you obtain an interval of occurrence, a sort of interval of confidence, and so you can associate to the parameter estimated by the open algorithm also one error. This is to follow the prescription at the beginning of not just the data, but also an error associated to the data, and also an information about the quality of the sample. Also, we perform in cooperation with Brian Cohen, famous is the book of Cohen, applying a different kernel for T1 measurement by progressive saturation approach, following not so complicated to obtain. It's possible to demonstrate this approach. T1, the kernel has this shape, and we modify the MUPEN 1D to fit this data to obtain this result. Last application was also to digital images. So Open has been, in this case, performed by a colleague of mathematics department, Fabiana and Germana Landi, also to deblur, restoring image using the same principle, open principle. Conclusion is a very simple, few conclusions. Now, in the remaining part, I show you the use directly of open. So I opening the software in remote work correctly. Ask. Open. Come faccio a vedere il mio? Can you see?
Sì, vediamo, vediamo.
Ok. Open. This one is the software. Open. I have a set, I prepared clearly a set of data for show you. Data was acquired using a Stellar console. In our lab, we are client and now friend, honestly, of Stellar since many, many years ago. And so we have a lot of instrument from Stellar. This is a mozzarella, cheese mozzarella, measured at two different time, day, 5 days of difference. The main idea was to evaluate what happens to characterize the change occurring in the sample due to the elapsing of time. So to have an idea about change the quality of the sample. This is the result of experiment. If you remember the slide I showed you before, we have in our lab, because our lab started working in oil field research, and so we need to measure core. Core is a piece of rocks, no, obtained at the bottom of the well in a reservoir, and this sample, the size is the order of 10 centimeter. So instead to use the typical test, NMR test probe of 10 millimeters, we have also probe, so coil of diameter of 15 centimeter to allocate, put inside directly a core. And so we can measure, and the result of the experiment, CPMG and the inversion recovery is obtained using a big coil. So we put inside, we measure directly a wall with the package, no? Mozzarella obtained. Mozzarella is here Roberto is the expert of cheese. Is a cheese when it's sold in the workshop is inside a package with the liquid. So we measure everything inside. To experiment, the first step is to have an idea about the quality of the measurement performed, and so it is a good practice to open. This is the one of the format of the old analog NMR Stellar console. Stellar data file is an extension, are in ASCII format, so it's possible to open the data and have a look inside and evaluate the quality of data. The typical structure of the experimental data consists of one header where you have all the information about the parameter used with the console in order to perform the experiment, okay, and then the data. This is one approach we can call low-level approach. It is often very difficult to have an idea about the quality of the data performed, just having a direct look at the data using some editor like this. And so in general, it's preferable to have some software. This one is a software we develop specific to browse the data to have a look. So we can work with this software, homemade software, open, for example, the same data, and using Zoom is covering the menu, so I have some problem. That okay, yeah. This one is a visualization, graphical visualization of the same data we have opened before using a notepad, etc. This one is a CPNG. The red is the real data, the fifth column of this. The second is the imaginary part, and the blue one is a non-exponential fit performed automatically by this software. Okay, apparently this is not a bad acquisition. It is not enough to have a look, a visual look of the data. It is necessary also to perform some computation to be sure. So apparently it's not so bad. We can open also CPMG, no? Is a set of data acquire a different echo time, no? In volume. So the distance between these 2 points correspond to the echo time. Echo time is, in this case, I don't remember, 1 millisecond, I think, because it's in microsecond, is tau below. Okay. We can open also the inversion recovery, so CPNG 42, inversion recovery 41. Have a look. Inversion recovery, you know, is a signal moving from minus infinite to plus m infinite. So there are two asymptotic value. And if it is correctly acquired, the negative value of monetization should be equal to the positive value. We can browse the software, and each point acquired to each inversion time of the inversion recovery, there is a feed. So is a multi-block inversion recovery. Each block is a feed acquire a different inversion time. Clearly, in order to understand correctly this, what I'm saying, it is necessary to have in mind the typical structure of inversion recovery. We can move on this and see there are, these correspond to when inversion time is so as a value, the monetization is null. Okay, you see the maximum value is very lower respect to the value at the beginning and the end, and then the final value, you see, is much bigger. Okay, okay, I need to move the menu of sorry, because the menu of Zoom is covering the menu of the software. I need to, if possible, to erase. Oh, no, okay, it's not possible. Fine. Perfect. Now we have a look to the data and start the inversion. We return on open. So we fit. Sto proprio un casino. Ok. We fit both the data. Before it is necessary to use some filter. This one is a internal full, is internal for just for internal use version of software of OpenWin, not the sold by Unibo. And these allow to read directly the stellar data. Then we can run a fitting. As you can see, the fitting is finished. Apparently, this distribution is composed by a big peak of around 30 milliseconds and a second peak around 1000 milliseconds. If you suppose this distribution is okay, you can proceed. But Open also give you a list of warning, and warning means are error not so dangerous. Beware means are dangerous. So, and these there is the list of all these um, performance parameter, no, computed by Open. In order to understand the meaning of this, it is necessary to spend a lot of time. We don't have, and it is necessary to read the manual to understand what this. There is many kind of error computed on the data in input and on the distribution and a comparison between these. Okay, we can go far, no? Go on this. We can also fit the inversion recovery. Version recovery another specific filter. This filter is more complicated because allow also to work on solid, not only on liquid. And when you are working with a solid sample, you have some specific behavior on the feed can be due to the dipole interaction of solid hydrogen. And so you have a opaque typical shape of the feed allowed to separate the liquid from the solid. This is another story. This is the effect of the filter. You see there is a convex behavior of inversion recovery, we told before, is composed of many FID. In this case, you can see there are stack of feed are added together to improve the visualization, but the convexity is opposite, means there is some dishomogeneity in the field, in the experiment performed. Perhaps the sample was not in the center, in the sensitive volume of the coil. Many can be the reason. Because this is a logarithmic scale, and if you represent in logarithmic scale a mono-exponential relaxation, you should, FID, you should have a line, okay? So this is far from a line shape, means there is something in the acquired data. In any case, we can continue. Now we can process also the inversion recovery. And we obtain this. In this case, you see, you have a very few warning. This one is typical because it's a specific procedure implemented in open with algorithm in order to detect error. And there is just a large noise, RMR. R is noise because it's in Italian, rumore, noise in Italian is rumore, Bob used the Italian word. This means the distance between the computed data and the measured data, point by point, is a little bit big. Big compared on what? With some specific internal, scompare cosa, internal value of the software, Bob calibrated on rocks. Remember, the original use of this inversion software was for rock sample, and so everything was calibrated, and so the software was verified and validated at the beginning, supposing to have a porous media which behavior is similar to rocks filled with water, oil, water, gas, etc. This fit apparently is good also respect to the open parameter to quantify, qualify the good of things. What is the next step? The next step is to look to the next measurement, CPMG inversion recovery, performed after 4 days. 4 days, yes, 4 days. Again, I repeat the computation of CPMG distribution and the computation of inversion recovery computation. Okay. Open on CPMG. CPMG, you see from the CPMG experiment, you obtain two CPMG can be computed, analyzed by Open because in this CPMG, the experiment was performed with two different echo time. In the using of T1, T2 filter appeared in the head. One was 205 microsecond and the second was 500 microsecond experiment. We perform on this. Again, you see, we have a large extrapolation, a lot of negative, non-negative constraint was applied, etc. And also for CPMG, you have a long list of possible warning and beware about possible distortion of data and consequently of the distribution. So CPMG, by point of view open, was not a good sample to be used. So it requires to be or remeasured or try open using software, field cycling software we looked before, and try to modify some sample, perhaps some wild sample point inside the sample, a queue, truncated queue at the end. You can also pre-process the data, the measured signal, relaxation curve in order to improve the quality. Consider that if you pre-process the data changes something, you are altering, modifying the acquired data. And this can raise some questions, no? If it is correct to modify the measured data. Also, if you have some outlier, one glitch in electronics during the acquisition, you have one point is many far distance from all the other. No? It is clearly due to something occurring during the acquisition. Okay, then we can also perform the inversion of open this. For this inversion recovery, instead open write some DAPS about the quality, and so also this inversion recovery. You see you have just also appeared a small peaks here, a very short time, 300 microsecond. This could be an artifact or could be an effect of the hardening of the evolution of the mozzarella cheese over the time. And so you need to decide, okay, this is an artifact due to the acquisition, due to open the inversion, or is a real phenomenon. And this is part of the research. You have to understand the easy approach, the correct approach is measure again with more attention the same sample in order to check if to have an answer to this question. The final use, what is compare together all the experiment. The result is this. Open, the typical output of open is like this, in which you have the inversion time computed and the, sorry, I have to show this is the time computed, this, and also what the amplitude corresponding to the time, both for T1 and for T2. So this one is more, and there are other information allow to evaluate the quality of the inversion. And then what is the last final just result is using some software to compare the two results. I have to rename because the output name is the same. This is 27 days. This is the result at 27 of July. This is the result measured and computed the distribution at 33, okay. Using some software, I use this, is also this homemade software, you can open these two and together compare the result for the two and decide something about is the real evolution of the sample, this appear, this disappear, this peak, for example, because this yellow is correspond, the color is not so good, can change color, is a little bit random. Okay, you see the blue as a amp here disappeared at 27 of July after 4 days. The total signal, the area below correspond to the amount of hydrogen in the sample. Apparently is changed, but this is strange. Probably in this experiment we lose at 70 of July some component for many reasons, echo time too short, etc., etc. And so the comparison is necessary to evaluate what is changed in the sample when you are sure the result of the experiment on the instrument and the inversion is correct. So your model, the parameter you have calibrated, estimated using open algorithm of your model correspond exactly to the behavior of the spin inside the sample. Just very, because time is elapsed, I'm late. There is also MUPEN 2D. This is for free. Also, these these are data from Gianni. I don't know, I can show, but I show. This, the run can take a while. This software is based on the MATLAB library, and is for free, the MATLAB library, and the last release is a little bit slow. There is a delay between start, and can take some many seconds before to obtain the result, but at the end will appear. You see there are a lot of parameter can be choose in order to fit are meta parameter because the algorithm is a open algorithm, 2D open algorithm, and so the parameter are self-detected. It take a while, wait. Molto vero, sì. Ecco. Is computing. Be patient. Ecco qua. Ok, the final result, T1, T2 maps, no? Con projection on the two axes and some information about the quality of the inversion, the residual, the Gaussian distribution, and so you can evaluate. The same is, for example, sì, ok, questo tutto, ok, the same is for model free. Model free is so MUPEN applied for analyzing, supposing the kernel is a model free, is for NMRD profile. Lentissimo, cosa gli viene? Okay, the profile, run. What you obtain in this case is a distribution of correlation times, supposing to have a multi-Lorentzian distribution as a kernel. Also for this In this case, you see there is also a Monte Carlo analysis in which you can evaluate the error to be associated to each of the correlation time computed, and so on. Also, this one is calibrated differently than open. This software supposes the input is composed of two-column data, very easy data, and a set of parameters. Also for this, you have a lot of parameters. You can choose to modify the quality in order to understand if distribution. This one is a comparison between the original data, and the red line is a model-free distribution compute fitting function computed by the software. Okay, stop. I finished. I'm late, so I suppose now should start Fabiana to describe more in detail, more theoretically correct, give correct information about the algorithm.
Thank you, William. I have just one question. Can you share the link to get access to these packages? I
Yes,
know where to
sure,
go,
sure.
but most of the people in the workshop, they don't know.
Yes, yes. There is also here a chat in Zoom, because I on above use Teams, so I am not comfortable with Zoom. Is there a chat in Zoom in which I can share the link?
Yes, it's down. There is a chat near share your screen.
I see. Okay, I see. I share now the link to all the participants. Okay, thank you for your attention. Allora, devo spegnere il microfono. Dove sta?
I think you are connected, so
Okay.
when you want, you just have to share your screen and you can start.
Can you hear me?
Yeah, we can hear you.
Okay. Can I share my screen?
Yes, you can share your screen.
I hope to be able to. Okay. Let me share the screen. Okay. Let me see. Which desktop should I use? This one. Okay. Let me share the screen. Okay. Can you
Yeah,
can you see it?
Yes.
Okay, so if I can start, first of all,
Yes, you can.
thank you. First of all, thank you everyone for Gianni in particular and all people here there. I would like I wish to be there, but it is not possible for me. So it's a difficult time now, and so I will continue in somehow. I will go back and I will present some of the mathematical background that is behind all the methods and all the software that William has explained just now. First, I'm Fabiana Zama, and my background is mathematical. I'm in particular a numerical analyst. So we met with Villiam and it's the physics group for the University of Bologna something like 10 years ago, and we started to cooperate together because we found that the method that it was used in the community of NMR as a heuristic and very well-performing method actually was interesting and we wanted to understand it better, and also at the end of a long story, we were able to explain its mathematical properties in such a way that we explain why it works so good. It's so clever, not only for the NMR problems that William have shown you, but also in other types of problems, mainly related on imaging and inverse problems. So today I will show a few mathematical insights about 3, let us say, building blocks. Perhaps the first 2. I don't want to be too late for the lunch. So okay. First, I want to say something about what do we mean from a mathematical point of view when we say that the problem is ill-conditioned, and in particular when this ill-conditioning comes from an ill-posedness of the continuous model. Then I will revise the mathematical framework behind the UPenn method, because UPenn heuristical technique is apparently so easy, but inside the background, the mathematical background that is inside and that is necessary to explain its behavior is not easy at all. And there are several very interesting points that we discovered later, once the method was already used from a long time. Then I will just explain, focus on one of the algorithmic blocks that is behind almost all the algorithms, almost all the softwares that are used in that William have shown you, and this is in particular related to the iterative solvers. So let me first I introduce just I reverse just a toy problem. This is an example of all the problems that William have shown you, but this example is an example, in one-dimensional example of what for a mathematical point of view is a Fredholm integral equation. This Fredholm integral equation is characterized by a kernel, which is assumed, and in this case it is an exponential decay behavior. So this kernel is regular, is continuous, and has many very good mathematical properties. So this integral is well defined. And also the known or measured quantities in this problem are related to the data, to the evolution times, tau, and to the data noise. The data noise is not, maybe it is not known, but it is assumed, because all the problems that we have seen are based on least square distances. And we use least square distances whenever we assume that a noise is a Gaussian normal distribution. Otherwise, for example, if we have Poisson distribution or other possible distribution, we still can model these types of problem, but we use different distances. And again, we were able to see that this principle worked very well also in that situations. But anyway, the unknowns, of course, is this function f of t and the relaxation times. Now I put myself in the linear case, or in the quasi-continuous case. Quasi-continuous because we discretize the relaxation times and we set them their values. This setting enables us to define this Fredholm integral equation in the discrete setting as a linear system. And so at the end, we have a linear model of our problems. If we don't set these times, we have a nonlinear model. We still have an ill-conditioned problem, but the condition is more involved to be analyzed. And so I just stay in this linear setting. This linear problem is characterized by this matrix, and we solve it as a standard nonlinear least square problem. Here you see the constraints. Usually we have constraints, at least positivity constraints. This is the reason why at the end we will end up with the iterative solvers. If we don't have these constraints, we might also avoid these constraints, and we have several possibilities from the algorithmic point of view when the problems is not too large, for example, in one-dimension problems. Anyway, this problem is ill-conditioned. This matrix is ill-conditioned. This is an ill-conditioned system. Why is it ill conditioned? We will see that we have a way to discover its ill conditioning, but the ill conditioning comes from the discretization of an ill-posed problem, because this is a Fredholm integral equation, and this equation is ill-posed in the sense that its singular values of the continuous operator have a decreasing behavior, and they have they tend to zero as more as we find a discretization of this problem. So what we have is an inherent difficulty, because as if we try to discretize in a more refined way this integral, what we obtain is a very an ill conditioning of the matrix that becomes more and more important. So at the end, once we choose a discretization, we can analyze the conditioning. And how do we analyze the conditioning? In this case, we have a one-dimensional case. We can think of computing a singular value decomposition, which is represented here. It is characterized by two orthogonal matrices and by a diagonal matrix, which contains on its diagonal the number of singular values that are different from zero, and it contains these singular values sorted from the greatest to the smallest. We have in almost all software languages have functions coming from the linear algebra libraries to compute this singular value. It is very expensive, and this is why when we analyze the ill conditioning, we usually apply it to one-dimensional problem or reduced dimension problem, because it is not possible to compute this factorization, this decomposition, when we have two large matrices. Anyway, we end up by defining the condition number as the ratio between the largest singular values and the smallest but non-zero singular value. And here is the problem. From a theoretical point of view, everything is easy. There is something that is not zero and something that is zero. But now, since this decomposition is computed, what we have is that these singular values will be different from zero. They can be simply they can simply contain the rounding errors, or they can contain more meaningful information. The problem comes when our singular value become as small as the rounding error because of the nature of the operator, and this is what happens in this situation. So we end up with a very ill-conditioned system, which means not only that this number is large, but also that we have a very small value here. Sigma r is very small, close to the value of the rounding error. So it becomes very difficult to distinguish it and to discard. For example, if we implement filtering techniques based on singular values, it becomes very difficult to discard it, to define where to stop where to stop and to truncate the singular values. And what is the effect of these small singular values? The solution exhibits artifacts. We can explain this by analyzing, by reminding that once we have this decomposition, the least square solution can be computed as a linear combination of singular vectors contained in the matrix V, and this part, which is a coefficient. This is a scalar. It is a scalar product of the column of the matrix U times S is the data, over sigma I. Sigma I are the singular values, and you understand immediately that if S contains some even small noise, then this noise is amplified by this ratio, and when sigma I becomes small as the for example the rounding error, you have an amplification of the error, and this makes the solution oscillating and unstable. This is just an example. Of course, it is a very small example. We consider tau as 146. This is taken from a problem in relaxometry problem. We define logarithmical uniformly distributed times in this interval, and we choose 100 of these times, And so we compute the matrix, and then we apply this decomposition. We compute the result, we compute the conditioning, considering the ratio between the largest and the smallest singular value, and what we have is this large value. But the interesting thing is in the analysis of the coefficients. What we see here is the set of coefficients. In the yellow line, you find exactly the modulus of the coefficient that we had in the previous set, so the modulus of these coefficients. And what we see is that these coefficients start to increase, have a large contribution, when we have the singular values that are these blue lines that tends to set at the value of 10 to the minus 15, which is of the order of the rounding error. If we analyze the error, which is the difference, the relative error, which is the difference between the true solution and the approximate solution, while as we increase the number of components into our solution, so as we increase I, we of course obtain a better approximation of the solution, and you see that the error decreases up to a value which is between 15 and 16, which is here. You see it is here, and then it corresponds to the increase, even if we have an oscillation, to the increase of the coefficients. Then it explodes. Not only it is increased, but it increases very fast, and which means that at the end, if you include too many terms, your solution is useless. And this explains, somehow I hope it explains, is an example of why ill condition problems are so difficult to be solved. Now I skip to the second topic that I wanted to analyze, and it is how UPenn, uniform penalty method, solves these types of problem. As Villiam has shown us, it solves these problems in many settings, 1 or 2 dimensional problems. So we can have very large dimension problems, especially when we have 2D discretization. So I represent these problems into a more general setting, more mathematical setting, where I define this linear operator as A, is a discrete operator. So actually it is a matrix which is obtained from the discretization of the linear operator. And we consider U as the object that we want to recover. E represents the discretization of the noise, and we assume that it is a Gaussian noise vector. And B represents the noisy data. The approach to the regularization, to the solution, so cannot be a direct approach. We cannot use any decomposition because it is ill conditioned. So what we do, we consider a variational approach, which means we transform the problem into the minimization of, let us say, a compromise between some part which gives us the data fidelity term, so tells us how our solution is close to the data that we are solving, that we are using, and something that regularizes, which means it assumes some properties, some regularity properties on the solution that we want to find. These functions are L, depends of course on U, and on a regularization parameter or a vector of possible vector of regularization parameter that is used to impose, to represent some priors, some properties that we want to see, we want to be reproduce in our solution. And we consider the possible constraint. It can be a positivity constraint, but it can be also bound constraints. So we consider a compact set that contains all the constants that come to the physical nature of the problem. We consider non-negativity here. If I have time, I will show you the algorithm that is used. But anyway, it can be extended to any type of constraints. And in this setting, uniform penalty, the UPenn method, is a multi-penalty approach in which we consider this function of regularization functional as a linear combination of regularization function where we assume that we have the contribution, local contribution of the discretization of the second order derivative operator, which means in one dimension it's the second derivative, in two dimensions it will be a Laplacian operator, and so on, plus an epsilon, which this is a value that allows us to avoid zero terms, but it is an important term at the end. This so is an epsilon term positive to guarantee that this function, this regularization function, are never equal to zero. They are positive, and they set that the number of terms is exactly equal to n, where n is the dimensionality, is the dimension of the solution. This is what is how we can represent the regularization, let us say, in a UPenn similar language. But now we have to see that this general approach has been, let us say, studied by different scientific communities, different and separate scientific communities. The, let us say, researchers that were interested in the analysis of porous media, and I say Villiam and all the, for us, the people of the physics department at the University of Bologna, but there is a big community of people involved in these studies. And they had developed these, in particular, starting from Brown, they had developed their solution. But let us say, in another setting, from the mathematical analysis of inverse problems, mainly involving medical imaging and mainly solving the problem in signal and image processing, there was something similar. There was something that the need to develop a regularization method with another language and with other purposes. So let us say we were able to put together the experiences of these two groups, and we will end at what we want to show you now is that we ended up with a mathematical definition of the definition of the mathematical framework of UPenn and the proof of its convergence. So from the NMR relaxometry, this is something that William has shown you. It started with Bob Brown and Borge and Fantazzini at the physics department with the definition of the uniform penalty method. Then it was defined in a software, and William has shown you the software and all the other software. We started our cooperation around 2016, and here we started by defining, recognizing that this that UPenn was a regularization method in the sense that it computed a regularized solution from a theoretical framework, but we were not able to establish the convergence of the method. And therefore, with this method, we had a heuristical procedure, very powerful procedure, that computed together the regularized solution and the corresponding parameter for different types of data fitting problems. All these were related to the NMR, let us say, community. In the same period, starting a little bit later, there was from the mathematical community, or let us say from people involved in inverse problems, that were also people from physics, but for other types of problems, that developed a method for defining, for example, the regularization parameter. These are quite classical methods. And among these, there was, let us say, a group of scholars that, starting from the 2010, developed a theory named as balancing principle. They were able to develop, they were interested in multi-penalty regularization, and their method, they were able to express from a mathematical point of view the need of balancing the amount of regularization and data fit. However, they were able to prove the convergence only for two regularization terms. But, for example, they gave us a foundation for defining the solution and the regularization parameter as critical point of particular type of functionals. And starting from this particular type of functional, extending this function, we were able at the end to develop our convergence theory. So this is what we had, let us say, at the starting. We tried to unify the two approaches, using the theory to extend the local, to extend the theoretical characterization to local component-wise regularization. We were able to recognize that UPenn is a particular example of balancing principle, and we were able to prove its convergence using in the setting of a particular family of algorithms, the maximization, minimization algorithm, that are very common in neural network optimization, and they are very common, and recently they are applied in this community. And so using all this stuff, we were able to prove at least the convergence. Now, I will not show you all the details, but I want to show you just the main steps. So first of all, we have this data fidelity term, and this is a least square because we assume that the noise is a Gaussian distribution. We were able to extend the Tikhonov, augmented Tikhonov problem, where we set, using a hierarchical Bayesian approach, we set the priors for the regularization parameter and the noise variance in this parameter tau. We added these two terms, and these two terms allow us to define this minimization problem with respect not only to U, but lambda and also the noise. Then, through an involved procedure, we write the first order of optimality condition of this Tikhonov function, and we obtain this system. This system is very similar to what our UPenn algorithm does, because you see that this system contains a setting of the regularization solution as the minimum of a function where the parameter lambda satisfy this equation. We have an extra parameter gamma, which is a balancing parameter, and we will see in a moment that UPenn somehow gets rid of this extra parameter. But of course, this is the solution. So what we say is that, okay, we have to solve this problem. This problem is a nonlinear problem. And the problem with, let us say, the background was that it was solved using the standard method for nonlinear systems, such as the Newton's or fixed point system, and they were not able to prove the convergence in any way, except for two regularization parameters. So when p is equal to 2, it is possible to prove the convergence, but this proof cannot be extended when we use a number of parameters that is larger than 2. And but it states anyway that the regularization parameter lambda I, each value, is the ratio between the residual and the regularization function psi. First of all, we can apply the uniform penalty principle. And now I state the uniform penalty principle in its building blocks, which states that all the penalty terms are uniform and have the common value. And this allows us to write the regularization part as the product between a C, which is this constant, and the number of terms. And the second building block is that the multi-penalty term is equal to the data fidelity term. So we define this C as the value of the data fidelity term. So what we have is that lambda I can be written in for each term as the ratio of these components. So this is the uniform penalty system. And so what you recognize is that now we have this gamma set as the number of terms, as the number of regularization terms. And again, now we have to solve this nonlinear system. And what we were able to find, first of all, we propose this algorithm. Actually, this algorithm is the UPenn algorithm, or at least it originates the UPenn algorithm, because what you recognize here is that we define iteratively an approximate solution of the minimization problem, and then we iteratively update the regularization term, exactly as you have seen from the Villiam algorithms. We can define a stopping convergence criterion because we know that it converges, so we can test the distance between the different regularization parameter to be sure that it converges. And what we can prove is that this algorithm converges exactly to the solution of the uniform penalty system. So what we have here, this characterization is actually obtained by this algorithm. And this algorithm contains what was heuristically used by the UPenn algorithm at the origin, at the beginning. UPenn is not exactly this one, because what we have is that UPenn, if you remember what Villiam has shown you, we do not have exactly this phi function here in this part, if I am able to define this, only this part, but what we have is a modified function, and we can generalize this UPenn algorithm, and this generalized UPenn algorithm is actually what has been used. So we have these settings, this modification of the regularization function are used to adapt and to improve also the convergence, but we don't to improve the quality of the solution. But we still show that this preserves its convergence, provided that the decrease of the function is recovered, but we were able to write it as a generalized UPenn algorithm. And to show, to finish this part, I just show you an example taken from the relaxometry problem. The matrix in this case is a Kronecker product of the two matrices T1 and T2, and so we have the two exponential kernels, and we can write it as the Kronecker product of the two matrices. We define a test problem by adding noise with a given magnitude. This is the size of the problem, so we have a quite large size of the problem. So the matrix is very large, and so we will need also to we will need to understand somehow how to solve this problem in an efficient way. But anyway, from our solution, now we can revise what you have seen in the previous example that you have seen from in the implementation of MUPEN toolbox. This is the, let us say, converging version, not converging. This is the UPenn derived from the balancing principle setting of the regularization parameters. Sometimes they are not optimal in the sense that give a quality of the solution that is not perfect. Even if they are perfectly convergent, they are perfectly defined from a theoretical point of view. A modification can be obtained in this way. For example, this is the classical modification. We add the information coming from the, let us say, the second derivative, and the first derivative filtered into a subset, into a neighborhood of each point. It makes sense only in one dimension, but especially in two dimension. This is the key point to obtain a good behavior of the regularization parameter. So we let us say we modify the regularization function for finding the optimal value of the lambdas, and we add, so we have this y tilde here, and we are modifying them. Consider that we are using only n and not n plus 1. We are ignoring the last one. And the last parameter is a ratio between the one norm, because in this case we add as a regularization term the part of the L2 norm and the global norm, which is the L1 norm, to make the solution, to improve the sparsity of the solution and improve also the characteristic of the characteristical behavior of the solution. We don't, so as you can see here, we don't use this epsilon here because we don't need actually. Then one norm of the solution is different from zero, provided that all the terms are different from zero. At least one of the terms is different from zero. And so this is from the mathematical setting that is behind the software. This is perhaps the same test problem that Villiam has shown you, just to show you that this B is the UPenn. It is perfectly, you see that it is not very good from there are extra components in the region, while the second one, the modified, allows us to keep a shape which is closer to the original one. And so this is somehow how we can tailor, we can balance these terms. So now this is for the convergence of our algorithm, of our UPenn principle. Then, okay, the last plot is interesting because we can compare the penalty, the -1, the behavior of the errors. So these are relative errors. We see the UPenn errors in black, so which means that this is the let us say theoretical initial value, initial method. This is the modified, the generalized method, which is close to, which is actually what we use in the practice, but we still preserve the convergence. And we see that this modification can also improve, in this case, also the convergence, makes the method faster. So we can actually, in this framework, and this is very interesting, we found the framework in which we can prove the convergence, allowing for the adaptation of these regularization terms to the quality of the final result. Now, this is the last topic, and what I wanted to show you is just something about the solution of regularized least square problem. You see here, I use just a single parameter, but what I'm saying can be extended in general to a larger number of parameters. So also to the UPenn value, to the UPenn method. We can, if the problem is small, for example, in one dimension, we can think of direct methods. I am not using the constraint here, so without constraints. And there are two classical approaches. I will be quite fast. What I wanted to say is that there is every software has its direct solver, the solver that to solve the linear systems. Using a smart and generalized singular value decomposition, we can include these solvers also into the solution, into our, for example, UPenn framework, where the value of the regularization parameter is changed because it has to be adapted, it has to be approximated. So, okay, very fast, this is the problem, and these are the normal equation that we solve. So this is the linear system that we would like to solve, for example, in this case. Of course, if you form this matrix every time and we factorize, and this is the case of the Cholesky, because the matrix is symmetric and positive definite, we have a cubic cost, which means that an n cube for each lambda update. If we are able to solve, to use the generalized singular value decomposition, we have faster updates, and we have to find this decomposition only once. Maybe it is not simply cubic, but we have this cost only at the first iteration. And this is what is used. This tool can also be used to analyze the conditioning of the problem, and it is possible to analyze. You see that this solution, so we decompose the matrix, we have functions that are generalized singular value decomposition, where we have one orthogonal matrix, U, and we have, two orthogonal matrices, U and V. We have a matrix X, which is invertible, and which contains the generalized right singular vectors. And we have two diagonal matrices, sigma and mu. This sigma is similar to the singular values in the original singular value decomposition. This matrix mu contains an identity and some terms that is related to the L matrix. You see that this is related to the L matrix. Since this decomposition can become uses only the matrix K and the matrix L, we can compute it only one. This is the fundamental property. So this is the reason why we have I here, because when sigma I is equal to 0, we have that at least the smallest component are equal to 1. And the shape of the solution is very similar to what we had in the singular value decomposition. It is a modification, it is a filter, because this is the second part is actually the what we obtain from the singular value decomposition. These are the singular vector xi, the columns, and this part is a filter factor. This filter factor, of course, is related to the lambda, to the value of the regularization parameters, but it is the only thing that you have to change if you update lambda. So if you change lambda, you don't need to compute sigma, mu, and all the other things. You just have to change lambda here and compute the update. So it is very convenient from the point of view of the direct solver. And this is the standard, let us say, is the efficient way to solve, to consider direct solution when the problem is as a small site and when you do not have constraints. If you have constraints, so you have, for example, iterative constant, or for example, if you have large domains, so assume that now you have large domains, you have a 2 or 3 dimensional domain, you cannot think of computing direct solution. And what we do, we base on iterative solution. In all our software, we find the conjugate gradient method because it has very beautiful convergence properties. The matrix M of the first order condition is symmetric and positive definite, so we can apply this method, provided that lambda is positive, but it is, and L is full rank, but usually the L is a regularization matrix. We can use the identity or the Laplacian if we are in 2 dimension, and we consider, for example, in UPenn, this L is the discrete Laplacian. The method, I don't explain the details, but it works iteratively. It updates the solution for a given solution L, so we have several updates. It computes direction and steps consequently. And for the computation of direction and steps, all what we need is just be able to multiply, to perform matrix vector multiplication. And since we have this matrix M, we don't need to form the matrix M, but we only need to be able to multiply the matrix K times a vector, matrix L times a vector, and they're transposed. So we can implement in a very, very efficient way. So we can implement it only in matrix freeness in the sense that not MV, but using what M has, so K and L. So we can avoid to form the matrix L. It is efficient from the computational point of view because from the point of view of the memory, instead of the storage of n squared, we have only n because we can perform this multiplication. We can avoid to form the matrix, and it can be used for matrices for problems that have a large number of unknowns. So, for example, in the case of 2-dimensional problems. The convergence can be an issue. We know it's well known that the convergence of this method depends on the conditioning. And the conditioning of the matrix is given by the singular values, or in the case of the generalized singular values decomposition, the value of sigma and mu. What happens in this matrix is that when lambda it becomes, for example, if you consider lambda equal to 0, what you have is the matrix K times K transpose. K is ill-posed, is ill-conditioned, and K transpose K is the square of this ill-conditioning, so it is even worse conditioned. So surely with lambda equal to 0, or with lambda too small compared to the smallest singular values of this matrix, because remember that the ill condition is due to the smallest singular values of this matrix. And so this becomes very bad. And of course, when lambda becomes too large, we have to have a setting of lambda, because if lambda is, let us say, greater than 1, to say is excessively large, then we might have an excessively badly conditioned matrix, and what we have is a difficulty in the solution of the problem, in the solution of the system. I finish with the case of constraints. So when you do not have constraints, you can use iterative method. When you have constraints, you have to use iterative method necessarily, but you have to add again this constraint in some way. We choose a quadratic convergence method, a modified Newton method, which is the Newton projection method. This guarantees fast convergence. The price to pay is that we have to compute a double iterative method. The main components of this method is the update of the solution, which is quite similar to what we obtain in the conjugate gradient. So we update f with the iteration L that goes on, and this solution is modified by a direction, and this is the Newton direction, a step, which is alpha L, a step length, which is set properly, projected on the positive orthant, because we are in this setting, we have a positivity constraint. To obtain the direction, we apply we solve the reduced system. This M is our normal equation system, but which is restricted to the set of inactive component. G is the gradient. We have to solve this problem. This is again a system which has a symmetric positive definite matrix, which is it is a restriction of the original one. And so in this case, we apply again the conjugate gradient, which means we have an inner iteration which contains the conjugate gradient. We have the outer iteration which contains the Newton's iteration. And then we apply this within a line search procedure to find the best possible step that guarantees the decrease of the value of the objective function, which is this one. So at the end, what we obtain is a method, which is the Newton projection conjugate gradient method, that this NPCG is actually the inner block of UPenn2D or MUPenn2D and so on. So we have this building block inside this, this method. This is the structure, and of course is the structure of this method. So we have an extra iteration here, we have an outer iteration, we have an inner solution by the conjugate gradient method, and then we have the steps of the line search. How do we stop these iterations? The first message is that the solution FL must be computed in a quite precise way. So we need to have very strict tolerances in this solution. So actually what we have, we set the Newton projection tolerance as this is what we applied in our solver. We set an outer tolerance, and we have to be precise. So you see that the tolerance range between 10 to the minus 6 up to 10 to the minus 8. You need to solve this problem precisely, otherwise you have a bad update of the lambdas, and all the regularization method fails. You are not able to make it converge. On the other hand, this is the standard Kurush-Kuhn-Tucker condition. It can be used you have to check the gradient conditions, but in our case it was simpler to use this relative error test, and so we didn't need to use this classical stopping criterion. And then concerning the residual based stopping for the conjugate gradient, we use this setting. So we set the residual, the residual of this, the relative residual. You see that we can have a larger tolerance, 10 to the minus 2 up to 10 to the minus 4. The price to pay is that if you are not precise enough, you have to spend more iterations. So if you are not so accurate, you need more iteration in the Newton's iteration. There is an adaptive strategy. We didn't implement it because it was easier for us, but it can be used. If you see that this is difficult, you can adapt. And the idea is that I can use user intolerance when I am far from the solution. I tighten it with this heuristic rule when I am near, in order to optimize the number of iterations. So this is the last building block. I won't show you any example because you have seen already. So this is, let us say, the mathematical and the numerical methods that are behind this all this software. So I hope I didn't annoy you too much, and thank you to all of you. I'm finished.
Thank you, Fabiana, for your talk. I don't know, maybe someone may have some questions.
I can have a question.
Okay.
Okay,
Okay.
Fabiana, thank you very much for this talk.
I hear an echo on your.
Wait, uh, okay, probably this
Now
problem is solved now.
No, yeah, yes,
And
yes.
in case one telling, sorry for my question, but if somebody, let's say, did not understand much from this lecture, because for instance, is from with biology background, or something like, something which is not so deeply into mathematics. Do you have any, how to say, message to take home from the lecture? I mean, what the person should pay attention to, what
Yes, for
a
example,
closed form message to
yes,
take.
I have to connect to what William has explained. William has shown you the softwares.
We do not hear you.
You don't hear me? Oh, sorry.
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 Yes,
We
I
hear you,
can.
so
Yes.
Okay.
Yeah, I can.
So William has shown you some examples, and he's shown you that there are several parameters to be set in all these methods, and you have to set them. So once you find some strange behavior, for example, in your solution, because they are too slow, or because the type of solution is not what you expect, or at least doesn't presents some unphysical features, and it always happens in a numerical solution of these problems, then, for example, in this case, you have to know that the tolerance parameters that you have into this method that are named as toll and PCG, for example, in the software, must be set, must be quite small. So if the standard, let us say what is the standard parameter is set to a value 10 to the minus 6, it could be a good idea for you to decrease it. And this is something that you can do by setting the parameters. And it's about the convergence of the behavior of this method. If you see, for example, that the values of the solution that you obtain is too noisy, in the sense that you see basically the error, you have to find a way to increase the amount of regularization, and so you have to act on the parameters that mainly William shown you, these beta parameters that are here. So I shown you an example that is quite okay, in the only example that I've shown you here, for example. Here I didn't put any parameter, but actually in the software you have parameters beta 0 here. This is named beta 0, this is beta 1 and beta 2. You can strengthen this quantity, you can increase them, and using these tools, you can move your solution, still being in a safe environment. From a theoretical point of view, you are using a safe algorithm, you will have a solution, but you can guide the characteristics of this solution by weighting in a different way the amount of the shape of the regularization function. Remind that when we need to regularize this problem, because these problems are ill-posed, which means that we might not have solution, or if solution exists, is not unique, you have to you use the regularizer as a tool to force the solution to go into a direction that you think is good for your knowledge of the physical problems. So you know the physical problem, you have to know the physical properties, and you have to guide. You can use these parameters to guide the solution towards the most physical solution that you can obtain. And this is quite natural. I hope I answered you.
Thanks.
Your mic is off.
I don't know.
Thank you.
Thanks.
you.
Thanks.
Hello.
Thank you, Fabiana.
We have just some
your
mic problems.
Okay.
Yes.
Let's meet later in 1 hour and a half.
Everybody needs to get some sugar for
Yes.
the brain. And okay. Thank you.
Yeah.
Hello. So I hope everybody can hear me. So I am Imran from Stellar, and in this part of the presentation, I will introduce all of you with our latest software platform and our data analysis technique. So I welcome all of you to Stellar. And the topic of my today's presentation is about Storm 6. So Storm 6, a unified platform